Hello and welcome back. So 5 minutes are done. So maybe we can start now.
Yes, just give me a minute. I try to join from my computer. So, okay, I am visible now. So this is a session where we basically see how to use the software, a little bit of it. Okay. I think we go here. Shall I start?
Yes, please go on. Please go on.
Okay, so far I assume that pretty much everyone is new to it. So how the software works and how you can use it. So after you will download the software, basically what will happen is that you will have an executable inside, and you get a license file, and then you just create a script file where you just tell where the executable is and where the license file is. That's all you need to know. And in my case, for example, I have scripts here which I run. Let's say I'm going to mostly use this one, and here I just tell where my solver is. You see, I have it in the build because I am developing it, so most of the time I'm using the one which is current, and where my license file is. Okay, so you can get a demo license file and always, and then there is this special character that you leave it because it will allow you multiple commands. So that is all to do, nothing else. You don't need any installer, you don't need to worry about anything. If you have a solver, executable, and the license file, you can always use it. All you have to do is just provide where they are. Okay, so typically how it would be used. So I assume when you have a problem in installing it, you can always write to me about seeing a problem. Typically, you will not have any problem because the solver has everything in-house. So that means it does not depend on any library. So it will not complain that this library is missing or that it is. Only thing that will be you will have a problem with is glibc library sometimes. But for that, we have something called memcopy. So this is basically a wrapper for the glibc functions, which you might not be able to find. And once this is in the LD library path, you will have enough. Okay. So you can run it on OpenMPI version 4 or 1.10. So now we go through some example problems, and in between, if you have a question, immediately ask, so that because I don't have too many problems, so the idea is that people ask the questions how it goes. Now, software has a GUI also, so I will use that, but typically my workflow or the people who are using it for some time, they just automatically set up, and then they basically change the setting. So in this case, let's say we have a mesh and we are doing a voltage shading. So we will set it up, and you can see that so what is going on in this command? So here, because this is first time, you can see. So this was my shell script, vec12.sh, which is where I put the 12 so that I know it's a 12 processor, and minus lc flow and the mesh file name. Now it's telling me that basically solver should set up a single phase flow for this. So if it was a multi-phase flow, I will use VOF. If it was a CST, then it will be flow CST, and then minus vel command is basically setting up a velocity at the inlet. So I'm setting up a very low velocity, 0.5 meter per second. And minus dt and the time step size is telling that the calculation is going to be transient calculation. And minus wd is for wall distance, minus kw is for k omega, and minus ppvtr is saying that I need for this a temporal post processing. So I'm going to create animation. And minus forces is telling that whenever there is a wall, please set up a force report for it. So I'm interested in knowing how much the forces will be. So in this case, you have a triangle in the center, and it will be reporting the forces. So you can report, let's say, you can create other reports also. You can create at the inlet, outlet. So a lot of advanced things are possible, but in this case, we are doing only a small amount. And this command till before this LC, the flow and mesh file and all, create a file called o.txt. Okay. And now o.txt is a journal file. We will see how it is. And you can run this journal file again to set up again everything, and don't have to give this command before. And you can modify this o.txt to make advanced setup. So it create your basic, and then you can add more things into it. And after that, you can go to GUI engine. So it's basically pretty easy workflow. But in this case, let's say first we run it and see what we come out, and then we check more things. So I take this case out. So how can I come out of this? Yeah, so let's say I'm out here, and this is my first test problem. And the mesh is given at the moment, but you can convert from the Fluent star CCM or a conform, so it's not going to be a big problem. And I put it the command here in the setup. So let's say I'm going to set it up. You see the flow, water shading, and everything. And this set me after simulation. And what does it do? It creates me this o.txt file. And the o.txt file is basically a journal file. If you are a Fluent user, you can see there are a lot of. Typically, this is setting up the simulation directory. It's creating a new simulation with this mesh name. Then creating a region set. At the moment, I don't give any other region, so it's creating the region set of all of them. In this mesh, we have only one region, so you can see the information. Where is this? So you can see there is only one region here, and the name is fluid, and it has a triangle which is of type wall. Outlet is outlet, inlet is inlet, symmetry is basically wall here. Okay. So you have everything information about the mesh here, and the mesh has a binary data which I will not open here, but there is a binary data which is happy. And so it created me this auto.txt file where I have more help here. You can see there are hints if you want to add the motion inside. So you don't have to go to user guide. You can just use the most of the things. Here I created a phase. Then I added the material from the air. You can change like water, and later on also change. It gives you a hint. Other material you can do like power law, cross, Karivya, Sudha, etc. It can be even solved. Or if you want a compressibility into the phase, you can add like idle gas, novel, level. It's a typical thing that you need actually. and then you can create a set out of this phase, and you see that we have a region set that we created here, and we created a phase set. So we can actually create physics model. So physics model, I say, okay, on the flow set and the region set, I create me a wall distance model, pressure-based segregated model. There is a post-processing model to help, K omega model, you see. Then it's setting up the simulation to be transient, creating a report, force report for it. And it's initializing, and then it's creating me the post-processing. You can see for the velocity and pressure. So now it will create me, I can reset, and it's created me a simulation tree file. Now, what is the simulation tree file? This is first time, so let's open it. Now I'm running the solver in a client server mode. Okay. So I know the port, so I'll connect it to port, and I can open. So you give information file, then you load the simulation tree, and you can see here also you can change things. So if you are a new user, this is how typically you will work. You can set up automatically, you can go and then you can change. So you see here, there is a region set here. A lot of other things are there. You can code a user library coding here. There is a support for BEFL, which are paper thin, like STL. You can just throw, if you don't want to mesh too complicated, you cannot mesh it. Just throw the STL inside. Then there is a support for Lagrangian, immerse boundary, partial precision. There are a lot of grid intersection. Okay. And for the phase, we created a phase from the air, and you can click here and change the material property if you want. So let's say if I make 0.22. Viscosity I can increase, for example. So you can change the values here. Okay. You can create the motion definition. If you are not setting it up from the script file, you can right click and also create. Okay. For the reactions, you can create the species, reaction system basically. Now you see there are models that we created just now. So this saves you a lot of time, that everything can be already set up. Now all the models, they are present in exactly same way. So you don't have to go to user guide to check again and again. So you can click here, and let's say I click here and I can select, let's say, higher order solver. So in WildKatze, to go to higher order is just one click. You click here and say select, and it's selected higher. If you want to, let's say, change the scheme, then I can put third order upwind. No problem. I can change other things. If you want to change under relaxation factor, you can change from here. So there are a lot of things you can change. If you want to change boundary condition, let's say go to the, all of them will provide in exactly same way. See, for the K omega model, the options are here. If you click on the flow, you get the flow model options. For boundary condition, you can see here inlet. And at the inlet, let's say I increase the velocity from 0.5 that I set up. I make it, let's say, 0.6. Okay. So I can change it up. And I can create more post-processing here. So there was you see force report 1, force report 2, report 0, report 1. That we automatically set up. Everything is set up automatically. You can just change the things. The simulation settings are here. Simulation type is transient. You can see we can change the time step size here. So a lot of detail, but you can see that you as a user don't have to worry too much about this thing. And now I change something, so I will save it. And I will come out of it. I can run, but this is my simulation tree file. I can open and I see that my delta t is 0.01. And my data export frequency is 10 to power minus 3. So it's not good, so I will make it a little bit bigger. Let's say 2 e to power minus 2. And I'm deliberately changing on the text editor so that you can see that you don't have to go to GUI. You can even change on the text editor. And yeah, yes, please.
Actually, the people who are new to CFD, so they typically understand it better if, just in console or Fluent, you actually have a screen where you see the picture and you click on it. It's a very primitive way, but do we also have that option here, or we
It
don't?
used to have that option, but then the problem was that the client have to have a VTK available, and this was a big problem because I cannot ask everybody to then compile the VTK and install it. So that part on the GUI is now hidden because most users who get used to the solver, they hardly ever open GUI. So it was not worth asking everyone to install VTK because of that, because it's faster. Once you get used to the software, you slowly, or maybe in few days, you get used to just opening on text editor and doing. I hardly ever open GUI, and any advanced users, they don't do, because here I can quickly change here. Like for example, I can change here also everything. You see here, higher order, I can go to second order and more. I can change here, so I hardly ever bother. That's why. But initially it used to be there. It's not that it was not like that. But the problem was again, compiling BTK is not so easy a job. And ask if you are a newcomer, and then I ask you, okay, in order to use GUI, you have to have BTK compiled and all. Probably you will not even use the software. So this is why it does not have.
Okay,
But
okay,
you can do everything from here. But it used to be like that.
okay.
So now I change that thing and I can actually run this. So the way I typically run, or you can run, is that I start the solver, and now you can interact with this. So I say pf run.txt. It created a file called run.txt also, which tells you the mesh file or S3 file. You can change this. So imagine that you have a new mesh and everything else is same, just change the name of the mesh. So that's deliberately created like that. So you don't have to set up everything again and again. Okay, so I will run it, and let's say run it for 500 iterations, and you can see it's going on, and it will be producing us some files. It's already started producing some template. This is already doing the button shading. You can already see. Correct. So it's very typical how you would see this thing. Let's see if it finished. It will be going on and on. I will kill it. Yeah, ask.
Yeah. So at the beginning, you showed a mesh file .bmsh. So what kind of so do we need to start off with a certain format and then it convert it while feeding it, or?
Yeah. That is right. You usually the users are Fluent or Star CCM or OpenFOAM users. How we work is that from Star CCM we have a converter library, so we cannot make it a part of WildKatze because the library is provided by CTADACO. But for Fluent, the solver can convert. So solver can just convert by Fluent to bmesh file and it will convert. From OpenFOAM, we can convert also, but usually the preferred way is convert from OpenFOAM to Fluent format and then use it here. So this is how typically we. The reason why we do like that is that we divide the mesh into two formats, like a binary file, that can be heavy, and the info file. You see here, this is a binary file, and then we have an information file, which is a bigger file, okay? Like that. Sorry, information file is just information. Now, if you have a very big calculation, like 250 million, and you want to set up on laptop and then send to cluster, you can do in WildKatze without loading the heavy binary data. So you just need the information data, and then you can say option minus no B mesh, and then you can just load it and run it. Okay, so this is how it can be. So this is why it's split it into. So let's do more cases actually, because I see that we are 24 minutes already. So let's run the second case. Okay. So second case is our car, which is very similar. So it's a BMW. So let's do the second case. Now in this case, I will not do anything. I just simply, so 28 meter per second is inlet velocity, which is like 100 kilometer per hour. Okay. Let's go up. If I go through them faster, then we have a chance to take questions. So I have a B mesh, and in this case the mesh is .ccmc. So there are. So I have a mesh coming from .ccm, and then there is this import. So I can convert the mesh from ccm to B mesh. You see now. So in this case, because you asked, I will convert, and it's converting me already. And I can go to the information, sorry. And I check everything is right or not because I converted. And you can see there's a car, outlet, and everything is given as a wall, so I will change them. The ground is wall, yeah, and the wall is basically also, in this case, I will. So you can see that now I have a car, I have outlet, inlet, and ground. So I will just set it up. So let's say, this is also single phase flow. So I will just give it a mesh name. Minus all distance, minus K omega, minus 28 meter per second, minus 20. So it does me the same. Okay, so now I have my simulation tree file, which I can quickly run. And let's run it because this we did a very similar calculation just now. I will only run 50 iterations because so that we can go to the next example. So yeah, here you can see that the solver is reporting few things, how many processors it's using, how many cells are there, it's like 0.9 million, and then the force reports are there, so all of the root and here it would be actually, should be reporting the forces residual. So it also reports cell quality, so that you know that there are, how many cells are there. So it did 50. Let's export the results. And we have to run by through that. And you can see that there is a wall distance here. And that is a simple car, and you see some flow field here. Can we car here? So, yeah, so this is your single phase flow. So when I exit, I will have the force report that it produced. Then I will have the residue. We just run it 100 iterations, so it did not converge very well. So this is another single phase flow. Let's do one more case. And this one is multi-phase calculation. Okay, so it's a typical Denver case. Now Again, in this case, I have a mesh in the fluent format, so let's convert it from the fluent format and then. So let me delete this file, these two things, so that we have only fluent format. Now the mesh is in fluent format, so I will quickly convert it. You see, it's converted. Now I can check my information, and everything is okay. Top is outlet, everything else is wall here. I don't do anything. Now let's set it up as a. So I will set it. This is actually still my setup shows. Anyway, I'll set it up. So that 12 what I said. Now I will set it up as a viewer and the mesh file. I set up let's say bt 1 into power times 2. I don't know what is correct one, but okay. And then minus pt vtr minus dr for the gravity, and I think that is pretty much it. And we have a basic setup. Okay, so now let's one time check what it has set up for me. And I can export the results and see what it did. Okay, so we can see the mesh also. And this is your typical dam break case in 2D. Just know that WildKatze is a purely 2D code when it comes to 2D, not like OpenFOAM and star CCM where you need a one cell thickness. You see, it's paper thin. It's just only 2D mesh. So we have a mesh which is like this. And now, if you see on this, you can see that the volume fraction is not initialized, it's everywhere 0, correct? So I have to initialize it correctly. So let's create that initialization. And the default initialization is usually done by the box, and I need to know the dimension of this box where I have to set it up, and I written it down here. It's typically and my export frequency I should change, let's say 0.1, because my delta T is 0.01 here. Okay, so now I am pretty much set up to do, and we can check the results out. Yeah, so load again. And we can check how this is set up. You see, it's a typical of dam break. So let's run it a little bit and see what does it produce. And just notice that I'm not checking any current number or anything, just run it with a constant AP, and I will not worry about the current number. And it runs for me, it will be producing. You see, already start to produce results. You see, it's already, it's too fast. So let's rerun it with a smaller delta t. So it's saying current number at the interface is 1.6. So let it run. Let's do it again with a little bit of smaller frequency. So I go to little bit. But a solver has no problem running even with a larger current numbers. Don't go. It's just that it was too fast to create animation, so let's slow down. So let's load it. We already have some. So now it's a little bit what you're used to seeing things. Okay, that one was pretty much done in a second. You see, this is typical of this dam break case. So I want one thing here, because I just now you saw that I run it with a 10 times larger delta t and the solver was still running. Now, typically in multi-phase calculations, even if the solver is stable, it doesn't mean it is accurate. So user has to be a little bit careful about the delta t that they choose. Okay? This can be a big problem, because if you are not good at judging the delta t on which you are running, you might get inaccurate result because the solver is able to handle that. In the other softwares, it will not run above the current number of 1 or so. So when it finishes the simulation, you are sure that the result will be good, because it forces you to run a very small delta only, and it take a lot of time, but the results at least you don't doubt. Here, even with the larger delta t, it will run, and then your results can be inaccurate. So with the practice, you will know with my physics what is the delta t that maximum I should go. Solver will go. I mean, you have to be careful. Yeah, so it's an advantage, but it can be disadvantage if you are not careful. So this is how typically I will not. So I think it finished. But you can see I run 500 time steps. The current number was 0.9 for the simulation effective at this moment. So typical of solver. We can change, if we want to have fun a little bit, I can change the DT on the command prompt. So, sorry, the time step size is here. And let's say 5 to the power minus 3. So we make 5 times larger. You can still and the solver will have no problem. That's a good thing about this software. Usually, if you increase the delta t like this, it will diverge in other softwares. Okay, so this is another configuration. Let's come out of it. Is there any questions now?
Yeah, actually, not exactly related to this simulation, but you have so many different modules. So, in case, so I think WildKatze is a closed source, right? So, do you have so two questions actually? One related to this AI training and all of these ROM training and all of these kind of things that are going on. So, do you need a different module for that, or even if you want to use multi-physics or you want to combine two different so as you showed, it's very easy to do it, but are there restrictions in a closed source, or it's just a one package, you take the license and or you just go on the dice hub and everything is open, you just pay for it and directly use?
Usually, each model has a license, but we don't differentiate it. I mean, even though each module has a license in the license file, if you look at the license file, it will show you that each model has a licensing. But there is a reason for doing like that, okay? Like, for example, if we develop let's say we develop a model for some company, they pay for developing a model, and they want only we want only them to use because they make it develop. Then the license will not be given to any other person other than them. So here you see the license has a feature, turbulence model, correct? So now the license file have all of them that you need usually, but except for the ones that are specifically developed for certain clients. That's the reason why it's a model based. So other than them, then nobody will be able to use that model. So if we work with some client and some company say, okay, please develop us something, and it's in our solver, but they don't want it to share. So that kind of thing. But you typically have the license file have all of them, like granular temperature models there, mixture particle. There are a lot of, so license file has, you can ask me also if you are doing a project and something new that can we do this, I can point out that this model does it. GUI usually have, when you set up from the GUI, it will give you the list of the models that are available. So it's not hidden. It's a typical models are you can just check. I mean, when you use it, you can interact and find out. It's not a big deal. But yes, it's model-based licensing. That was one thing, and the second thing is with the, if you are doing with AI training and all, then the automatic setup will help you a lot in doing automatic setup and all. So let's do one more last, because the time is running out. One last setup, that is our shell heat exchanger. I kept, because this one is a little advanced, and here so this will be the last one, okay? So after that we talk, ask questions too. So you see there are 6 regions in this, and it's a typical of your heat exchanger. And what's going on is that there are, where is that? There are 6 regions, and some of them are solid, some of them are fluid. And obviously in the fluid region we are solving the flow. And in the solid regions and the fluid combined, we are solving the energy. So that's the idea. And the 2 fluid come with the 2 different temperature. One side the 500 degree Kelvin is coming, another side 300 degree Kelvin, and the heat will be exchanged. So that's typical scenario. Now, in our case, we have 10 intersections, grid intersections. Now, typically you can manually define them on the GUI. You can go right click and define. You can also do it from a text file. So I create just ggi.txt file, and then you can do that. And in this case, I am not setting up from the command prompt in a normal way. I am setting up from a configuration file. So I have a configuration file because it's a little bit advanced setup. So now what is going on is that you first create a region sets, and now you see the framework in the action. So you create a fluid regions for water 1 and water 2, so there are 2 tubes. Then you have a solid region where you have the cap from the both side and the shell, and then you have a solid region set for the tube sheet. Now why we are doing this is that because the material property is different in these solids. That's the reason why we created 2 solid region tubes, solid regions. Because one of them will have a tube property and one of them will have a solid property. So this is the reason. So we created a flow phase, we created a fluid phase for the fluid, and then for the solid for these ones, and then a tube phase for the tube property. So basically material property, how we are specifying. And then we are telling this phase to region set is that I have 3. Fluid phase is giving the properties to the fluid region. Solid phase is giving the properties to the solid region, and tube phase is giving to the solid tubes. Now, it's so simple to do it here. If you are in open form, you will be crying because how do you maintain this and that? But you see, this is why the framework helps. It's simple to do that. Then you add the material. By default, I put air and then overwrite it with the density, viscosity, etc. Okay, so in this case, when there is a solid, the viscosity is almost 0, and the thermal conductivity, specific heat and thermal conductivity. And this is saying the grid intersections are given in this text file. and it's saying that, okay, create me a flow model, energy model, then change the settings. So now you see from the configuration file, I'm already specifying what velocities I want. At the inlet 7, I have 1 meter per second, and the temperature is also changed here. You can see one side the temperature is 500 degree Kelvin, and another side is. So I specify everything here. So that's why then I don't have to write on the command prompt all this thing. Basically, then just one time with a peace of mind I can set up, and I can just set up from the configuration file. And how I will do is that I will just create an o.txt file. Oh, sorry. So let's see, come out of this and go to other. So let me do it again, copy from here. So it's create me o.txt file, okay, at this moment. And sorry, this is my o.txt file. I'm not changing anything, but I can add more things into it if I want. And then I will just run the o.txt file to generate my S3 file. And my setup is done. So it's pretty simple. It cannot be more simpler than this to set up. So you see the solver is doing some grid intersections at the moment. And we are done. We can run it a little bit. Let's run it just 50 iterations. Ideally, this case will take like 200 iterations to properly converge, but I will just run 50 first. Yeah, so by the time it's running this 50 iterations, if there are questions, I can answer them.
Yeah.
Yeah.
Yeah, actually, when you have these two different kinds of two or three different kinds of regions, so does the software allow us to easily assign different amount of workers, or I mean, is that sort of modularity present?
Yeah, you mean the partitioning. So
Yeah.
what is going on this way, we have, I would say, not so great situation, because we do the partitioning region by region. So each region is partitioned into the number of processors you are saying. Correct. So basically idea is that each region is equally divided, then it will be balanced. So if you have 5 regions and each one of them is, if you are asking to run, let's say 12 processor, then each region is partitioned into the 12, 12, 12, 12, 12, so it should be balanced, correct, ideally. But it can end up in a situation where one region is too small.
Right.
Okay, not have, so it cannot have less than 12 cells then, correct, one of the regions.
Yeah.
So that is the problem you can have. But overall, my experience is that when you have a calculations like this, when you have so many intersections are going on, and they are usually difficult calculations, and the client is happy to get the result out.
Yeah.
So because the solver is far more efficient anyway, so even if it may be inefficient in partitioning, but it might take, let's say, another 2 hours. But you get the results out, that's more important than I have an imbalance and I wait, let's say, another 10% time or 30%. So usually, so this works out. So yeah, but yeah, it cannot have a perfect, that's the problem of providing a general multiphysics software. You cannot have a perfection in the speed and partitioning it. Because once you focus on that, then your software has to give up a lot of other things, and the client want to actually have the result and accurate results. It does not care whether it can, I mean, he might care, but in many cases it's better to have a result than have no result.
Yeah, absolutely. Absolutely.
Is okay. Yeah, so we can run, let's say, but solver makes up, like for example, VOF calculations. We are typically like 5 to 10 times larger delta T and etc. can take and more efficient. Then if you are 10% slow per iteration, let's say, it does not matter if you are able to do it 5 times efficient anyway, even after. So, like the dam break case that I run just now, I just increased the delta T 5 times. You try doing that thing in OpenFOAM, for example, in a complicated calculation, it will not run. It can happen like overnight run and boom, it diverts. And then you are starting everything again. We don't do it statically. In the solver, you set up and you run, you will get the results out. So now in this case, let's say we have the results, and let's see the results for this case. There are more cases, but we are kind of running out of time, so let's quickly check this thing so that we have some time to take up questions. So this is your typical, and it's basically, you can see it's a polyhedral mesh. And you can extract. Let's extract our tube sheets. So the tube sheet, let the temperature on it. I can create a mid plane. So on the mid plane we can see velocities already, and the temperature. One side it's coming from here and getting heated up, correct? And the other side, let's say we and you can see the fluid that is coming from here getting heated up here, coming out. So that's typical pressure. So yeah, so this is typical of it. When I came out, it gave me the residual, and the temperature is pretty flat now. It's almost there, within 50 iterations even. No, it had how much? Let me see. It had like 1.7 million polyhedral cells. So yeah, I think we are pretty much on time. So let's have like 5-10 minutes of questions. There are. Yeah.
Hi, I think thank you for your very informative session on this. My question is regarding that max GPC algorithm, what we got as a maximum gradient compression algorithm.
Base. Yeah.
Yeah. So where you show that we have like a sharp interface over there. So
Yeah.
we're getting from 0 directly 1. So calculating that we get accurate like a more faster solver area, but we are missing any physics over there, like because we directly calculating the properties over at very sharp rates. So is there we missing any physics over here, or we wrong calculating the physics over here?
Well, the interface in real life is very sharp already, correct? So for example, if there is a geometric scheme which is trying to create even sharper, like I said, vectors, trying to create a plane, sharp plane, and then dividing into the two, like that. So what happens really is that when the interface is sharp, like in this case also, it's very sharp compared to isolate vector, like that. The properties change abruptly, they change very fast. So high density to suddenly low density. The water is 1000 and then the air is 1.22, and viscosity also changes very sharp. So sometimes it becomes numerically more difficult. So imagine that you have a scheme which is more smooth, then it becomes numerically easy for the solver. It may be not good for the results, but the smoother transitional from in the volume fraction is much easier for solver to handle than the sharp. So it's a kind of like a double-edged sword. You make it more sharper and then you suffer as a solver. So a solver has to have to be extra, but we don't miss the physics more than what the discretization brings. You know, if the discretization errors are there, like for example, if there is surface tension. Now, surface tension cannot be balanced so well. It's a well-known fact. So you will, yeah. So more sharper it become, more difficult to then it become with the surface tension. But the solver is robust enough to handle. We have done validations and all. So yeah, it is not missing the physics. It's just changing the new stiffness of the top. You can say. Yes.
Okay, thanks.
But MaxGBC has been now in the solver for like 7 years or so, and we used it for many commercial projects and giving very good results right now.
Okay, thanks.
Yeah, more. Yeah.
Yeah, any restriction on the on the HPC side, for your basic license or
No, no, you can, once you have a license, on the demo license there is 64 process, but it's just for a demo. If somebody want to use more process, just let me know. So for individual, we'll not change that much. Just the demo license that we'll provide it will have 64 process, but typically a normal person is not going above that, correct? But if you want to, when you take the license, you can run with any number of process you want, or any calculations you want. We don't check. We never check that part. Not like a CCM or that you have to be everything very strictly monitored. That you cannot run more process that the license allowed you. Not like that. The solver will not check if you are running, let's say on the same license you are running 2 calculations at the same time. Solver will not check anything.
So sometimes actually even like clients have questions about security and some policies, etc. I mean, this is nothing to do with CFD, but sometimes that is why they don't go to cloud and like that.
Yeah.
So any safeguarding or any policies regarding that?
No, we just provide the solver. Then you are not giving the data anywhere. No? So and there is no installation also. So you can just run the solver on your own place, just like any other thing. If you are worried about the data breach, because usually what happens is that there are license manager nowadays, which are, let's say Star CCM is one of them, where it need internet to constantly check it. We don't do that. So the solver does not try to interact outside of your system at all.
Okay.
It does not try to send any messages anywhere to check the license. License is inbuilt in the executor. When you provide a license file and the solver matches what is compiled with it. So when there is no license manager, it will just simply check the executable knows this license or not. And if it knows, it will run, and if it does not, then it will tell you that license is not valid. But there is no license server. We don't try to send any information on the internet. No connection to outside world.
Great.
It will not complain if you take the internet plug out. In fact, my machine where I run it has no internet.
Okay.
More? So if there are not many more questions, then we'll slowly wrap up. Please check Dice Hub, actually. And also you can write to me. And the current version is available on the GitHub link. And the demo license you can ask me, or if you have registered with Jaydeep, you can just send him the message.
Yes, actually, Arjun, I think you are already on the mailing list. So maybe you could also share the link, and so people could directly go to the.
No, I do one thing.
file.
I send you the demo license actually, and we can just set the link to everybody.
Okay.
they want
Okay.
to try.
Yes, sure. Okay, so thanks a lot, Arjun, for giving us the time,
Yeah,
and it was really a very informative session. Also, very inspiring. Just 1 minute, if you have, like,
yeah,
since
I
I
have a
start.
lot of time.
Yeah,
Yes.
I mean, I wanted to do this for the students actually. So any advice you could give to students or anybody who is new to CFD, how they should proceed? Because right now there are a lot of information, coming on the internet from so many different directions.
Okay,
So,
this is actually a good question, but I'll tell you what happened, my experience, okay, because I've written so many CFD softwares, pretty much all type of CFD softwares I have written.
yes.
So if you are trying to write a finite volume solver, let's say just for learning also, even if you use, I will recommend only one book where everything is mentioned and given. You don't have to look anything outside to write this software, even this or Star CCM or Fluent type of software. That is below one Paris book, okay, that computational fluid dynamics book. That has everything that one needs to write a CFD solver in finite volume. You don't need to check anything. Every discretization process, everything is been covered. And I was lucky enough to be introduced to it in 2004 by my professor at that time. And I did not have to check anything else because everything is there in that book that you need to write a fully working unstructured grid solve. If you check nothing outside, you can still write the whole thing from the scratch. So if you want to learn how to write CFD softwares and all, there is one book that I will recommend is this one. I will not recommend because this is the book where it mentions how the commercial softwares are doing, like how WildKatze does, what Star CCM does, or Fluent does. That is pretty much what we follow because I've been a developer, so I can tell you that this is how we solve it. So everything that WildKatze does is pretty much mentioned in Professor Perry's book. I also learned from there. It's not that I did not, but if you are a student and you want to learn this, because many times we have a question: what does the commercial softwares do behind the closed doors? They don't do anything special. But they do it right. So I learned also a little bit later that stability actually comes from accuracy. So like, for example, the solver is very stable, but you see when you compare, it's also come out to be very accurate because once you do the discretization correctly and then all the errors, when they start to go out, then everything converges well. If you have not done things well, then the solver will not converge because it cannot converge, it cannot conform to the equations that you are trying to solve. And there is some bug somewhere, God knows, but that can hinder your convergence. So once after initial stages, the stability comes from actually accuracy. It's a very interesting phenomena, but this is how it is. So people many times they say, okay, it's a commercial software, it's stable, they must be adding something into it and all. I can tell you, I don't know about the Fluent, but with Star CCM and the WildKatze, we're not doing anything special. Other than the only thing I think WildKatze is doing different is that cell quality aspect is inbuilt in. That means if your smash is bad, then it can limit the gradient. It will not limit the gradient, but it will go to first order up in scheme.
Yeah,
Okay.
yeah.
So it become more stable. It's aware of the cell quality. But the Star CCM, you have to enable that part.
Yeah.
You have to say, okay, enable the cell quality remediation. Then it will do. Without, by default, it will not do. But WildKatze will first check what is your cell quality. And if the cell quality is bad, very bad, like flat cell or something, then it will not try to use a higher order or second order. So, it makes sense also. If the cell is so bad, why would you do it?
Thanks, Arjun sir. Thanks for all of your guidance. Also, it will be very useful to some of my students who are here. So so thanks Arjun for this wonderful session, and we will share whatever you are giving on the mailing list.
So
Yeah.
Tukarab asked, the book is about Milovan Peric,
Below one.
computational fluid dynamics. It's a very popular book. Please check that. If you search for the most popular CFD books, it's one of them.
Okay, thanks. Thank you.
Surprisingly, many people don't read that book. It's very surprising to me, and they keep searching how to do, but everything is mentioned. And in fact, when I was developing my code, I actually followed even like wall treatment, everything, exactly how the book mentions. Yeah.
Great. Okay, so so if there are no more questions, then we can just wrap this up. And his email is also there. You can connect with him on LinkedIn, where I
Yeah.
came in contact with him. So thanks for attending the session, everyone. Thanks for staying for 2 hours. So I hope you will make good use of WildKatze. So will it be launched on Dice Hub very soon, or it's
Yeah, it
already
should
there?
be this week. I'm
Wow,
hoping. it
great.
should be.
So great. So I want to be one of the first people who tried. So yeah, thank you.
Yeah.
Thanks a lot.
Thank you,
Thanks a
Daniel.
lot. Yeah.
Bye.
Bye bye. Yes.
Thanks. Thank you.
Thank you. Thank you.